you are straight up partying at the rock show here, but you're a little close to the speaker. It's getting a little loud. You need a break here. Your ears are starting to hurt, so you back up. And my question is, it sounds like a stupid question, but I don't think it is. Why does the sound seem softer when you're farther away from a speaker compared to when you're close to a speaker? And be careful, there's actually two distinct reasons for this, so let's make sure we're clear about this. It's not so dumb of a question. Here's a speaker. Now this speaker is going to emanate sound waves out away from it. And I'm going to represent that sound wave like this. Let's draw a circle around it. Here's the sound wave. Now to make things simple, let's just say it sends out one burst of a sound. It's not sending out repeated sound waves. Let's just say there's one burst of a sound. So this is what the sound wave looks like at a given moment, the wave front. And if you wait a little while, that wave front's going to emanate outward. So here's the sound wave after some later amount of time. Here's the sound wave if you wait a little longer. And if you wait a little longer, the sound wave might look like this. These are all the same sound wave. These are just at different moments in time. And so the question was, to remind you, if someone's over here, close to the speaker, why do they notice a sound that's louder from a person over here farther from the speaker? And one reason has to do with what's called intensity. The intensity is defined to be the power per area. So this speaker is sending out a certain amount of power, and that's divided by a certain amount of area. So right here, that power is divided by this much area. That power is spread out over this much area. But this sound wave is going to emanate outwards, and that means this power is going to get spread out over a larger and larger area. So now that same amount of power is spread out over a larger area. And this keeps going. The further away the sound wave gets, the larger the area. So if you're way back here, now that same amount of power is spread over a much larger area. And this is one reason why the sound's going to get weaker, because if you divide by a larger area, if you take that same amount of power, you divide by a larger area, that intensity is going to get smaller. And your ear, notice, your ear doesn't sample the whole wave. Your ear just samples the part that actually gets into your ear. If your ear could hear the whole wave, if you could sample that whole amount of power, yeah, maybe that would sound just as loud, but you only get a piece of it. So you're just measuring how concentrated that sound is, not the total amount of sound that is on the whole surface. So how much less is it going to be? If someone's standing twice as far away, so if this person's at a distance d from the speaker, and some other person is a distance 2 times d from the speaker, twice as far. So for this person up here, if this person hears an intensity I, what intensity will this person over here experience? Will they hear half I, fourth of an I, an eighth of an I? To figure it out, you've got to remember that these sound waves are emanating in 3D space. These are 3D sound waves. So these are really spheres. These are spheres of surface area that the sound wave's emanating out along. And so, got to remember what the area of a sphere is. I remember the area of a sphere. It's 4 pi r squared. This means the power up here is going to be, so power is going to equal, or sorry, intensity is going to equal the power divided by 4 pi r squared. This means if you're twice as far away, this person's twice as far away, he's twice the radius away. That means the area that the power's been spread out over is now not just twice as much area. This is r squared. Since this is r squared, if you double the radius, you're getting 4 times the area. So this is actually, the power over here is spread out over 4 times the area. Since the same amount of power is spread out over 4 times the area, this intensity is going to be 1/4 as much if the same power is spread out over 4 times the area. And if you were 3 times farther away over here, what do you think the intensity would be out here? The intensity, since you've got 3 times the radius, you square that 3, you're going to get a factor of 9. This is going to be 1/9 the intensity out here. So this is an important rule. The intensity is going to be proportional to proportional to 1 over r squared. Lots of things in physics are proportional to 1 over r squared, and intensity is going to be one of them of a sound wave because it's spread out over a sphere, and that sphere gets bigger like r squared. So this is actually a little bit of a simplification, but this is one reason why the sound waves get softer the further out you go, because that sound, that power, is now spread out over a larger area. It's an oversimplification because, let me show you why. It's an oversimplification because if you had an actual speaker, now an actual speaker is probably not going to be sending out perfectly spherical sound waves. Whoops. I mean, you wouldn't really want, if you're going to manufacture a speaker, you probably don't want the sound wave traveling back here just as much as if it travels in front of you. You want the sound to go in front of the speaker. But it doesn't even matter. Even though it might not be a perfect sphere, if it's going to be part of a sphere, it's still going to emanate along part of a sphere. This is still going to be in 3D. These are going to be 3D sound waves, and so even if the area isn't spread out over exactly 4 pi r squared, maybe this is only a third of a sphere, or maybe it's only an eighth of a sphere, or a 16th of a sphere. It doesn't actually matter. What matters is you're still going to have r squared here. And because you're going to have r squared, that intensity, that intensity of the sound wave is still going to be power divided by something with r squared. So the power is going to be, the intensity, excuse me, is going to be proportional to 1 over r squared. It's going to die out like 1 over r squared. So let's come back here. Let's come back to this one. So that's one reason why. One reason why the sound gets weaker, that power is distributed over a larger area. There's another reason why. The other reason why is that I lied again a little bit. This power gets diluted over a larger area, but this power, some of that energy doesn't even make it over to the second person. Some of that power gets lost. Some of that energy gets lost into the air here. Now, I don't really like that term. It doesn't really get lost. We know where it is. But energy is lost, and by lost we mean it gets turned into thermal. Thermal energy of the air molecules in here. And so it's not really lost, it's more like it's just unavailable. It's just stuck in the random thermal vibrations of the air molecules. Now I'm not talking about the actual coordinated oscillations back and forth of the air molecules as sound passes through. I'm talking about just random vibrations in random directions of the air molecules. This takes energy away. So this is one more reason why this person farther away will hear a softer sound. Not only does that energy get spread out over a larger area, some of this energy gets lost. And this has a specific name. This is called attenuation. Attenuation is referring to the fact that some energy gets lost to the medium itself. So whenever energy gets lost to the medium through which a wave is traveling, we call it attenuation. So these are the two reasons why, the two independent reasons why the sounds will sound softer. One, that power is spread out over a larger area. And two, some of the power doesn't even actually make it to where you're at because it gets lost due to attenuation in the medium itself.